For this course is I'll be exploring the convolutional neural networks for active noise control. So active noise control, or ANC, is a physical model used to control which noise is important in a given environment. This physical model uses two microphones: the primary microphone, which takes in the audio source, and the secondary microphone that analyzes this audio source and produces an anti-noise signal, which is used in combination uh, to dampen the noisy environments and amplify important signals, auditory signals. Such models are used in the development of hearing aids, in which we want to mitigate the use background noise and amplify speech. Additionally, in the film industry, these models are used to combat the negative effects of using an IMAX camera. Since IMAX cameras are really noisy, it's hard to record what the actors are saying. So using an active noise control system, they're able to dampen the noise captured from the IMAX. This model is used to dampen noise produced by the IMAX camera and only capture the speech spoken by the actors. From the papers that I've read, there seems to be two main ways to create this anti-noise signal. The first way is through the selection of noise itself, right? Using deep neural network models to segment and classify each component of the audio source and select the one that you want to remove and produce an anti-signal for it. And then the other method is using an anti-noise generation, in which that the model itself, the neural network model itself, generates this anti-noise signal, which is then used to dampen the audio source. Previous neural networks models and the state-of-the-art ones utilize a U-shaped model that incorporates an encoder-decoder with a LSTM. Another version is a hybrid spectrogram testnet, which is a LSTM based model that's mainly used in classifying and segmenting the different components of music, right? So separating the guitar from the piano, from the vocals, etc., etc. Right. Overall, I've seen that the two main models used for active noise control is CNNs and LSTMs, right? The main usage of the LSTMs, the main reason why LSTMs are used is that they consider long-term audio dependencies. However, this is under the assumption that the source of the audio is in one place. If the audio source moves, these long-term dependencies become harder to calculate, right? And furthermore, the papers I read that use the CNNs consider this moving audio source, but are limited to, well, convolutions. So they have hard time trying to generalize what the anti-noise signal should be. So for my project, I'll be exploring the D-Noise Net, which is a deep CNN model that utilizes an MLP to fine-tune the anti-noise signal, and this neural network model is used within an ANC model, right? Where PZ is the primary source audio taken from the primary microphone, and SZ is the secondary source produced by the secondary microphone, and F self considers the nonlinearities produced by the microphones themselves. In other words, these microphones tend to saturate the sound, and this layer helps mitigate this error, mitigate microphone produced errors. Additionally, I'll be exploring the use of a burn layer, which adds noise during training and is used as a model stabilizer using scaled random noise, in which a layer with a normally distributed noise value between 0 and 1 is element wise multiplied at the last layer of the CNN. So my project goals is to try and improve the dNoiseNet model using the burn layer and other acoustic analysis methods. I will be processing data using the SPIB dataset, which is a dataset of audio recordings with very noisy environments, such as airports, constructions, and automotive-related sound. I'll be testing the model efficiency, so both speed and accuracy, and to test how this model will work in a real-life scenario, I'll be generating a room based on the paper illustrated by JB et al. And that's it.